Well, hello, everyone. Thank you so much for joining us today. My name is Erin Judge. I'm the Assistant Director of Alumni Engagement at the College of Engineering and Applied Science. I'm excited to be here today with Associate Professor of Computer Science Chris Heckman for this next webinar in our alumni webinar series. As part of this series, we aim to showcase some of the amazing research that is happening at the college and bring our faculty directly to you for an exclusive look into their groundbreaking work. Now, it's my pleasure to introduce Dr. Chris Heckman, Associate Professor in the Department of Computer Science at the University of Colorado at Boulder and the Penn Co-Faculty Fellow in the College of Engineering and Applied Science. He earned his Bachelor of Science in Mechanical Engineering from UC Berkeley in 2008 and his PhD in Theoretical and Applied Mechanics from Cornell University in 2012. He also held a postdoc at the Naval Research Laboratory in Washington, D.C., and was recently a visiting academic with Amazon's Scout Robotics program. Professor Heckman's research focuses on autonomy, perception, field robotics, machine learning, and artificial intelligence. He directs the Autonomous Robotics and Perceptions Group, which aims to develop practical and explainable techniques in probabilistic artificial intelligence. His work in computer vision, machine learning, and sensor fusion has applications to intelligence, defense, and environmental monitoring. Professor Heckman, thank you for taking the time to share some of your work with our alumni and friends today. I'll go ahead and turn it over to you.
Thank you. And thanks everyone for coming. Like Erin mentioned, I'm excited to talk to you a little bit about what we did at the DARPA Subterranean Challenge. And as people are settling in and wondering, what I'm going to talk about, I want to share some footage from this recent project of ours. The goal of the challenge was to develop robotic teams that could explore natural and built underground tunnels, caves, and mines in order to find objects of interest, which we called artifacts, and build maps of the environment. So implicitly, this was a multi-robot exploration mission with human-robot interaction as a supplemental component of it. The challenge started in 2018 when we were selected for funding as part of the competition by the DARPA, the Defense Advanced Research Projects Agency. And we had a year to go from having no coordination between our proposers team and the different groups and research students that were involved to have to spin up a fully staffed $1.5 million a year project. Few PhD students were interested, but we had a core of a few that were intrigued, and the competition made up the bulk of their PhDs. There were 3 competition deployments. The first was a limestone mine outside of Pittsburgh. The second was an abandoned nuclear power plant south of Olympia, Washington. Then the final event was in an underground constructed course incorporating elements of various elements in the middle of Louisville, Kentucky's mega caverns. And besides those competition deployments, we had many practice deployments on our side. So the finals course was quite challenging. The scale of the course was enormous. Large caves augmented onto the constructed course, narrow caverns with challenging terrain elements strewn about by DARPA. And to live up to the tagline of what's called DARPA Hard, the competition included a fully constructed subway ticketing station, platform, and tunnel about 100 meters of length inside of it. The single human supervisor wearing the orange helmet in this image was the only individual on the team who could interact with the robots once they were past the starting gate. The interface of how the supervisor would interact with the robots was up to our team, as was how that interface would actually communicate with the robots. So essentially, as soon as the robots are in, we're the ones in charge. And only this one human supervisor can do anything associated with teleoperations or communications with the robot. So we had 15 minutes to set up the system when we arrived on the course. So clock started ticking, and we only had 15 minutes to set up this desk, all the robots, get them ready to go, and then start pushing buttons to make them go inside the cave. And this simulated what a real-life disaster response might look like, is the idea. So here I show some photos from the final event. This consisted of testing, team meetings, and a lot of discussions with the other teams. At the conclusion of the competition, our team finished 3rd place globally and as the top American-led team, eking out a win over teams led by the Jet Propulsion Laboratory and Carnegie Mellon University, but placing behind teams led by the Norwegian Technical and ETH Zurich, as well as the Australian CSIRO, which is a Commonwealth government-funded group. We were able to walk through the course afterward and observe the artifacts we missed and the enormity of this built structure that DARPA had set up. And what is most notable here is that we did win this cash prize at the end of it, supporting our research going forward. Our team's name was Marble, so there we are on the leaderboard there. Our team was composed of many individuals over the 3 years of the competition. Here's a list of the teammates who participated in the final year of the project leading up to the final event. So there were more people than what were listed here, but this is the final event team. My research group has their names highlighted in red. So you can see that there were enormous numbers of personnel from the research, just my research group, that were part of this team. And we roughly split up our team, this Marble team, into groups of engineers and technicians building platforms, another of scientists and engineers developing autonomy solutions, a few folks focused on comms, and then a group of project engineers, which were PhD students, and the principal investigators providing management on the project. So I'll focus on the platforms and autonomy for the next few minutes to outline our setbacks, solutions, and lessons learned. I won't have too much time to talk about our comm solution, and we have that listed in some papers, but if you're interested, I'm happy to give some discussion to it in the Q&A. So first of all, these are the platforms that we used, and we changed platforms over the course of the competition, those 3.5 years or so. At the top right of the slide, you'll see a couple of different names: Styx, Tunnel, Urban. These were the different events that we had to participate in, and you can see that we actually had only a few platforms that, one platform really, that stuck around from the very beginning to the very end, but then in the middle, there was quite a bit of thrashing and determining what the final platform loadout would be. In the end, we had 2 of each one of these robots, 2 ClearPath Husky robots and 2 Boston Dynamics Spot quadrupedal robots. So the Husky robots here were powered by a large computer, 64-core Threadripper that was inside of this little enclosure there. It had beacons that were sitting on the back, and then that would enable us to extend our comms range. And it was a 4-wheeled robot, which means that it has some pretty good clearance, but it can't really go through very challenging terrain. It obviously can't go upstairs. And we replicated essentially the same compute structure and perception systems like sensors on these Boston Dynamics Spot when we got that, when that was made available to us and when we acquired them from Boston Dynamics. We were able to miniaturize a few of the components to fit it onto a backpack form factor that was mounted on the back of the back of the Spot. But you can see that actually in the end, we had very similar types of sensors and logical computational components that were part of this. These 2 Spot platforms were really remarkable platforms, improving our capabilities here. So one of them was that it obviously allowed us to travel up and down stairs much more reliably than in previous iterations where we couldn't do that with just the Huskies. But also the Spot was remarkably able to traverse more tortuous terrain than the Huskies. So while the Huskies might get stuck in mud, the Spots had no such challenge. They were able to sort of step through many different kinds of cases, and even on rubble, which was pretty remarkable. It also walked about twice as fast as our Huskies drove, which meant that we got larger coverage faster than with our Huskies. On the negative side, though, the Huskies or the Spots don't really allow for as much payload as the Huskies do because of the wheeled vehicle configuration. So we were unable to put any kinds of beacons and comms extending capabilities on the backs of the Spots. So really, they were just fast recon types of agents, whereas the Huskies would be deployed after the Spots and then help extend the comms range by dropping those beacons. We also deployed an unmanned aerial vehicle stack that was tested and actually worked quite well, but it could only launch from the gate, and the way that we architected our software made it so it was difficult to launch from the back of the Husky, which means that we could only launch these UAVs for about 10 minutes from the gate. So we ended up not deploying those at the final competition. Some conclusions from the platforms in this slide that I want to mention here is that some features of what we would like to accomplish in robotics is they're conditioned on some very deep design decisions. So for instance, I mentioned that we weren't able to launch that quadrotor from the back of the robot. And that was because we had architected our software in such a way that transferring all the knowledge of where the robot was and what it had done in the middle of a competition was not exactly easy. And that was sort of like a software engineering challenge that we faced. So we didn't expect that. That was sort of a lesson learned. The other one is that terrain traversability is an enormous problem still in robotics. In many cases, we'd like to deploy these wheeled robots because they're simple to control and easy and sort of expected behavior. They can't fall. On the other hand, a more complex system like the Spot with well-engineered terrain traversability capabilities was actually able to make us move much faster And so that was sort of a buy versus build argument that in the end, we sort of went with this spot that was able to really work very well. I only briefly mentioned the sensors, and many people are interested in this, so I wanted to give some discussion on this. There were a number of sensors that were involved in our final loadout, and this is essentially what the loadout was for those sensors. We did not have sensors that were all around the robot, like in many self-driving cars you might see. We had a single, what we call the sensor perception head, and on the very top was an automotive-grade LiDAR, and that provided us 3D mapping capabilities, along with an inertial measurement unit, an IMU, gives us very short-term motion measurements, which are unreliable in sort of longer term, but helped in building a better map from the LiDAR. And there were also 3 cameras on each one of our platforms, giving us greater than 270-degree field of view perception, being able to see what's around us. So that's essentially what we built our artifact detection capabilities on, just using standard off-the-shelf computer vision tools to determine what objects are in a scene. And those object detection tools are an outgrowth of deep learning capabilities in computer vision over the past 15 years. So the artifact detection system was entirely based on this notion of what's called gigabit Ethernet vision. So we didn't have to use USB for cameras. That was really nice. We also had a couple of these LiDARs at the bottom. Those LiDARs provide us low to the ground understanding of what the geometry is. So that gave us like, oh, there's a rock here, maybe we should avoid it. And since this automotive grade LiDAR doesn't really look down very well, you can see that it actually kind of has like some of its field of view might be truncated as a result of that plate, that metal plate there. We had some pretty cheap LiDARs just facing downward to make sure that we could see if there was anything that was terrain hazard as we were driving through. This is just like an idea of how the mapping worked. And I kind of want to give like at least one little deep dive here. So this mapping capability was pretty remarkable. What we did was we built out these volumetric maps as shown in the bottom right. And these maps had a couple of different pieces of information they conveyed to the robot to help decision making. First, they told us where geometry was, right? So there's a wall, there's going to be an open space, there's a floor that we can drive on. This is all as a result of that 3D LiDAR that was building this volumetric map as it was driving through the scene. But we also integrated a few extra capabilities here. We looked at what are traversable and non-traversable terrains, and we marked those in the volumetric map based on how jagged the features were. So if something was like really, really jagged or bumpy, then we wouldn't want to be driving a Husky on it. Maybe the Spot could do it, but not the Husky. So we had different definitions of what was traversable based on these sort of like high frequency features in the geometry of the scene. We also had other types of object detectors going on, for instance, like stair detection, which is really easy to see in a geometric map like this. So we had this capability of saying, oh, there's a set of stairs here. So maybe the Husky can't do anything with that, but the Spot could walk up it. And so we were able to do some map sharing as a result of this labeling between the different robots. And so what was going on was points went in, we had a terrain classifier and a stairs classifier, different types of machine learning techniques to be able to fuse those into a labeled octomap. And we shared that capability with, or that information with all the other agents. And that enabled quite a bit of unique planning, as I'm going to show in the next slide. But the conclusion of our final system was that we had some map data with some contextual encoding, which supported planning. Let me give you an example of what this looks like. So here's a little video of 2 robots starting in the same place. The first one's going to naively explore in this cave. This is the Edgar Mine up in Idaho Springs. And it's going to go through a cavern, sort of go back because it's just exploring. It doesn't know where to go. And then it says, okay, I built this map. And it's conveying all this information, mapping information to that other agent. And the other agent is then saying, okay, well, now I have this prior map. It showed up in purple. I can use that information to be able to support my planning, but also to disambiguate different types of paths that I should go down. So agent 1 can go down its way, and agent 2 can sort of look in a different direction. So I wanted to, there was this human-robot interaction component. This was the main interface for that. I showed it in the previous slide where the orange helmet supervisor was looking at a window. You'll see here that there's many different buttons that the person could push, right? It's basically, there's all these different agents relaying different information. Oh yeah, there it is. Yeah, so apparently CU just decided to test its emergency broadcast system, but now it's stopped. So what you see here is the different types of buttons that the human supervisor can push. Things like give a new waypoint to a robot, or take teleoperator control, or read me everything that the robot's seen in the last 5 minutes. These are different like low-level controls that the human can interact with on the robot. Plus, I mean, this teleoperation capability is pretty remarkable. We were able to actually support, because of our good comms network that we built out with using these beacons that I have described, actual real-time operation. So if there was one robot that wasn't really doing the right thing, the human supervisor could take over at that time. What that then resulted in was actually that the human supervisor was pretty busy, but not too busy through the competition. So here's a little flow chart, if you will, of the different times that the human had to intervene and what was the main purpose for that intervention in each one of these cases. So there was a launch of D02 first, D02 standing for dog number 2 on Boston Dynamics spot, so looks a little like a dog. And the human had to actually teleop the robot through a narrow cave because the robot thought, this is too narrow for me, I don't really want to go down it. And the human supervisor, for some reason, thought, no, I want to make that robot go down it. And there were a couple other cases, like a stair alignment issue and being able to go through fog, which is a really challenging problem if you're using vision-based techniques. And so what you'll see here is on the bottom line of this chart, the human supervisor, whenever there was an orange patch, was actually getting pretty busy, had to do something that took all of that person's attention. That's where Dan had to maybe directly interface with the robot or override autonomy. And Dan, this human supervisor, I mean, I just want to give a shout out to him. He really did an incredible job. He's an Air Force colonel. He was on our team. He was doing his PhD with Eric Frew at the time, and he was the only human supervisor that we really trusted to do this. He was able to do multitasking in a sort of specialized way. So what you maybe take from this chart is that the human was pretty busy, but didn't have any conflicting obligations as a result of his interacting with the system. So he didn't have to interact with 2 robots at the same time. And there were some statistics that I could give you. There was about 9 minutes per robot on average that the human supervisor had to interact with the robot. And the entire system had a mean time in green, or mean time in autonomous state, for all robots about 3.5 minutes, which means that every 3.5 minutes there'd be some emergency that the human supervisor had to respond to using that interface that I previously showed off. And so this is like a map of what this looks like. Dan was able to sort of go through about 50%, 60% of the terrain of the whole map, which actually still scored us as many points as I mentioned and made us still, emerge pretty victorious in this competition. So at the conclusion of the final event, this is sort of like lessons learned. There was this, what's called a PI roundtable, a principal investigator roundtable. And many of these PIs asserted which problems from the DARPA Subterranean challenge had been quote unquote solved. Okay. Many areas were asserted to be solved that I don't think I necessarily agree with them, some perhaps, but I think that overall the DARPA Subterranean challenge was a good lesson in what we can do, but we're not ready for prime time yet. And why do I say that? So here's one example where the robot's standing here for over 2 minutes, not doing anything, not moving. And it may be waiting for human input, calculating a plan, trying to resolve a perception issue, like calculating a loop closure on a map or something. Either way, it's wasting precious time, like 2 minutes of just standing there. So I would say that agility in this problem is still not solved. We don't really have great on-the-fly decision-making on these robots. And this, by the way, was the first place team in their final round. So that's just one example. Another was this. This is that environmental disturbances still aren't solved. So this is a second place team. And here's their UAV flying in this warehouse area, and that piece of paper was caught in the downwash from the quadrotor and just crashed it. And so we really don't have a great idea of how to solve for like what happens when something in this environment is doing the unexpected, right? So reasoning over these types of challenging like disturbances is part of the problem here. And I'm not going to claim that the other teams have all the problems. Here's our robot standing there for a while, so it actually nearly tripped there, as you saw. And it's not really going anywhere, doing anything new, right? It's kind of just like following some programmatic planning exploration strategy. And here's it in the exact same place 2 minutes later, and it falls over catastrophically. So, there are many issues related to like decision making here that still are unsolved. And this one, in my opinion, is like a terrain issue as an example. So, here is the final like course score, right? So the top placing team scored 23, which means they found 23 artifacts. And the second place team, same, but they did a little slower, so they lost. What a bummer. That was really a bad beat. And there's us, Team Marble, number 3, right? And what is the untold statistic here is that all of these numbers are out of 40, which means that, fundamentally what we're dealing with is like 23 out of 40, valves were turned off, or 23 out of 40 people were found. And so this is really not an acceptable proportion of this is not what I would call victory, right? I would say it's a strong start. And it's certainly a proof of concept. So I have postulated, and my research group is very interested in what were some of the challenges here. And I've already mentioned a few, right? Terrain being one of them, decision making being another. And but another is this human robot interaction component. And I show you this picture again to demonstrate to you that this interface that the human had to interact with was not really what we would expect from squad-based tactics when we're doing some search and rescue mission or anything else in subterranean caverns. And so what we would normally expect is, language, drawings, things like this, not really kind of like this very inelegant click button kind of interface. And so this has motivated for us some new work that we're doing in natural language understanding and how we integrate that to embodied robots. And just one example of here, the challenges involved with this problem is go to the blue bin on the left of the red backpack might be a request made by a human supervisor. That's a kind of like, that's a very specific request. It may not be as natural as some people would expect, but let's just take that like spatial referring expression plus vision type of problem. And how do we rectify the language with the image? Okay, so we're making some kind of referencing in this image for the robot to go and follow something. So this is not purely a natural language understanding task. This is some kind of grounding task, as it's called. So how do we ground objects in the vision with the symbols or the objects that have been invoked or mentioned in language? And obviously we all know that when we see the image and we see the request, we can identify that there's this blue bin there if our monitors are tuned just right and it's not too dark. And that there's this red backpack that's helping with the relative spatial referring expression, right? So that is acting as an anchor in the image that we can reference against the language in order to identify which bin we're talking about. All right. There are also queries like this one, where it's like, go to the chair on the left. And there might be some ambiguity there, right? We could be talking about this chair. We could also potentially be talking about this chair, right? And so there might be some disambiguation that needs to request human intervention or further specification on the mission. And so these are just types of problems that exist. They sort of span natural language understanding, perception, understanding the image, and then maybe even some logical constraints. So what we had developed as a result of just trying to solve some of these problems is a first step in, we believe, a unique way of being able to address this for embodied robots. And the sort of idea that I'm going to be playing with for the next few minutes is that we might have a robot has some vision, so it understands, it has some pictures of what's around it, and it has some query, something like a firefighter needs to put out a fire, find something to help with this. And then instead of trying to solve some sort of tightly coupled, how do I deal with the image and the language at the same time? There is some work in machine learning that's involved with that. How do we develop different systems that can play together and then take these arbitrary queries and be able to resolve objects that are in the image as well as those that have been referred to in language, right? And the way that we're doing that is by actually having a large language model generate code for us based on the instruction, that it can run functions, run commands on the images, and be able to extract knowledge from the image, and then eventually make the robot do something, have an execute plan at the very end, so a command that can be run to make the robot go somewhere. So how does this work? It's kind of like it's, in my opinion, kind of an elegant solution. And so we have the maps as previously stated. I've already shown you some of those maps that were built from LiDAR. They're built online, so we don't have any prior information about the scene. The robot has the LiDAR. It's kind of running in its own course. There are these visual inputs, sort of like one-shot visual inputs. They're like, what are the images seeing or a camera seeing in images right now? Okay. And then we have the command, something like go to the person sitting down as an example, right? And so what we want to do is be able to identify that person in the scene and then be able to relate that to the maps and give waypoints or give an idea of where the robot should move based on that. In order to do that, we rely on this code generation layer, which is actually ChatGPT. It's the API version of it, but there's a sort of nice little Python interface that we can use for this. It's not going to the website and typing something in, but it is ChatGPT, the engine that powers it. And we feed the entire navigation or robot API to ChatGPT, a 7-page prompt at the very beginning. And it's things like navigate to object, and then there's an X and Y coordinate for the object. And there are things like find an object, at which point we run a different type of model over the visual inputs to find the list of objects that might be responsive to the query. And other types of functions like this, things that the robot can do, right? So a 7-page navigational API that we've developed for our robot passed into ChatGPT plus our prompt, something like go to the man sitting down, okay? And then code is generated that is essentially like asking what is this query asking? What is this person wanting me to do? Find a person sitting down. So I have to look at my visual inputs and I have to go and say, where is this, maybe there's a person, maybe there's a man, maybe there's a woman, maybe there's some other kind of not person label, but something. And then I need to essentially do that disambiguation. Like if I was requested to go to a person, but all I've detected is, man, is a man a person? You can see that that's not, that would require this context-based reasoning. And so that intermediate layer is the code that is generated plus waiting on different visual and map inputs. I can then from there even like look at things like what is left of, right of, and run other types of function calls to say like, is this X coordinate in this image to the, negative compared to this other image or this other coordinate, and that would imply left of as an example. And I'll show you a quick example in the end. This uses the visual input system uses a different model. It's not ChatGPT because we're not talking about language now, but it's something like it. It's called an open vocabulary object detector. In this case, we used GLIP, and it extracts objects specified in the command. And then the last thing is that we extract that bounding box, we project it into 3D space using this Octomap, this previous map that I had talked about. And then we use a very basic path planning module, something that's been researched for decades in robotics. And so this is not an end-to-end system, right? It's developing a way in which we can take the natural language instruction and integrate it into different components of robotics that have been well understood for a long time. And so, yeah, this is sort of our approach. Now, I want to give you a quick example of what this code looks like. So if you'll bear with me for a second. This is actually output code from our 7-page navigational API plus query to ChatGPT. Okay. And in this case, what's going on is it's saying like navigate to the tree was the prompt. Okay. And so you can see that the code that is being written by ChatGPT is things like, okay, I'm going to create an empty list of detected trees. I'm going to look over this image that I see right now, and I'm looking for something called tree. Image patch.find is something that we defined for it, but it knows that it needs to use that in order to be responsive to the query. And then it says, if there are detected trees, sort them by their horizontal position, left of center, right, middle, whatever. And then if it was go to the middle tree, then I'm going to look for something that is most responsive middle tree by actually dividing where are all the trees in this image, find the one that's closest to the center coordinate. So it's actually running these mathematical commands for us because it realizes in order to meet the middle tree specification that I'm going to have to find something that's sort of the left bound, the right bound, find the one in the middle. And then, then navigate to it. Run this function, go to the middle tree. Here's the bounding box to the middle tree, and then you can go ahead and, do the math to figure out where the waypoint is. So that's just one example. And I think that you know, it's pretty crazy that it does this. Oh, I have to then sort the trees. I'm going to write this pretty complicated Python function to be able to do that. And to me, that was like you know, this is capability that no one could have expected, I think, from ChatGPT at the outset. So what else can we do? Go to the middle tree is pretty basic, right? But I wanted to use it as a sort of expression for how the different types of mathematical functions in Python can be invoked by something like ChatGPT. But if I want to really use the power of these capabilities, it's something like go to somewhere where I can watch a movie. Well, it's a context-based prompt, right? Where is somewhere you can watch a movie? Well, it's a TV or a monitor needs to be nearby. But that's only part of the story, right? It's not just because there's a TV or a monitor, it doesn't mean you're going to watch it there. So we actually do the detection of the TV, no problem. That's okay. Right there. Our object detector can determine there's some sort of thing that I can watch a movie on. Okay, so a TV, a screen, these are screen patches. That's been done. Okay. But it also says, well, if I'm going to watch a movie, I better be sitting down. So it looks for a couch or a chair that's nearby the monitor or TV and then says, oh, you want to go somewhere to watch a movie? Don't go to the TV, go to the chair nearby. And so that's kind of what this is doing as well. It's determining what is the distance between the chair and the TV, is an appropriate distance where someone can sit down, and then go ahead and, you know, return where the chair is. So these are sort of, you know, remarkable outputs from this. So I want to show you a video of how it looks like, because this is not purely an object finding task, right? It's actually running the calculation of like how do I get to the place? And so that was the robot going to the chair that is near the TV. And here's some examples of what these results look like. So in case you're interested in how well this works, we ran quite about 100 samples, 100 different prompts. And we sort of classified these in a fairly, what's becoming a standard way in robotics, what we might call generic prompts, what, like, you know, go to the doors. Specific, go to the left door. Okay. Relational, something like go to the left door that has something in front of it, right? So, and then contextual, go to somewhere that you can go outside. And then a qualifier, we didn't do that for our single agent case, so I'm just kind of focusing on that one right now. The code generation capabilities for ChatGPT in these applications, in just GPT 3.5, which is like the older version of GPT now, were pretty remarkable. You know, 100% in generic prompts, down to about 66% in these contextual prompts, like go to somewhere that I can go outside. It might not get that code correctly, exactly right. GPT-4 is much better, unsurprisingly. So the performance on GPT-4 is, you know, at least 100%, where G3.5 is 100%. But then on contextual prompts, it's much, much better, 20% improvement. Or in this case, yeah, 20% improvement. So that's the code generation side. The object detection, which is something that people generally think is like done. Like we have object detectors. We've had object detectors for 7 years. In fact, in these cases, the object detectors in open vocabulary are not very good. So what we're seeing is that there's pretty reliably a 20% drop in performance in this leaky pipeline of code to go to thing that is focused on, can I find the object in the images? And there are a few reasons for that. But the biggest one is that open vocabulary object detectors are like, you know, things that use unsupervised methods or like self-supervised methods are still in their relative nascency. So I think that there's a lot of research that is still to be done in looking at object detectors there. But then the rest of this I want to just point out is like waypoint to execution, waypoint generation to execution is not very leaky. So the robotic side of things is pretty solid. It's really the reasoning that has to be developed further. These are just a couple of examples, different maps that we were looking at. Head towards something that can help firefighters, run to the person on the ladder, walk to the rightmost cone. These are all things that can be pretty reliably solved with GPT-4, as long as the object detector can see it. And here's just another example of, you know, or a sequence of examples, drive to the man sitting on the table. And I'm showing you that there's this 3D map that's being developed and waypoints are being dropped. And that is what is giving rise to the capability to do planning, right? So here's the person sitting on a table, walk to the white fan, and et cetera. So the thing to note here while you're watching these types of examples and the robots sort of traverse the scene, is that we're using these large language models in essentially what is called like a zero-shot framework. We're not doing the training. And so that means we're heavily reliant on the capabilities of like OpenAI's ChatGPT to be able to do this determination for code generation. There are capabilities that we can leverage going forward to look at how we fine-tune these models, which means that now we're going to be owners of the foundation models, and then we have to ask what kind of data we put in. There are many complicated questions that one could answer when it comes to like how we train foundation models. I'm happy to talk about that in Q&A, but for what it's worth, in these examples, we used sort of somebody else's model. We did not do the training ourselves. And just in case you're interested, because remember the Marble, this Subterranean challenge problem was actually a multi-agent navigation problem. We extended our framework to be able to give instructions to individual robots, and then have also some capability of doing delegation between robots. So if you had to do a multi-agent task, like one agent go over here while another one goes over there, then we've extended that capability based on our prior work. And so these are just some examples, and I kind of wanted to give enough time to chat about all the different things that we're doing and maybe some of these foundation model discussions. But this is where we're going with our work, and we're really excited about the capabilities for natural language understanding for imbuing better robot autonomy. So here's my group, and these are the PhD students and postdocs in the group, and some of our sponsoring agencies. And with that, I'm happy to take questions. So thank you.
Thank you so much, Professor Heckman. We do have some questions that we can go ahead and get started with. And then to everyone on the webinar today, please add your questions to that Q&A button that you'll see at the bottom of your screen. Just to kick us off here, we had a question come in from Sam regarding the part where you were sort of explaining how robots would explore the terrain that they were in and create a map. So he's clarifying, when you say you have Agent 1 and Agent 2 for map sharing, are you deploying 2 robots for this exploration?
Yeah, so in the Subterranean challenge, we deployed 4 robots. And so that's why I was giving those 4 bars, and finally, like the human supervisor given a bar like a robot, although was in more capable a position than the robots. So there were 4 agents, and there were 2 spots and 2 huskies as part of that loadout. They all shared maps with one another when they were in communications range with one another, as extended by those beacons that we were dropping, and we were building a little mesh network as we were going. So that was just one capability that we had to, enable multi-agent coordination. In reality, like we could have potentially added one more robot, maybe, but there probably would have been more demand on the human supervisor's time. It could have led to that catastrophe I was talking about, where 2 robots need a human supervisor at the same time. But for the most part, yeah, we tested with 4 robots in almost all of our deployments. Hopefully
Great, thank you.
Yeah.
Another question that we had come in from Kevin: what inspired you most during this work?
Yeah, so the DARPA Subterranean challenge is definitely a very compelling exercise. So there's a challenge when it comes to operating in underground environments. So you're GPS denied immediately, which means you need to have very accurate localization. But we also want to be able to give situational understanding to people who should not be going in as the first responders in some of these dangerous situations. So it's one of those dull, dangerous, and dirty tasks that we are really focused on as a robotics community. We're not looking to solve problems that don't scale well, although that is the interest of some automation researchers. Autonomous robotics researchers are trying to solve problems that just humans can't or shouldn't be doing, right? So another example is like exploration, sending robots to different environments that might have longer sort of communication times than currently available. So they need some level of autonomy. Europa, a moon of Jupiter, would have something like I think it's like an hour light round trip, which means that teleoperation on Europa is not an option. Versus on the moon, it's fine. It's just a few seconds. We can kind of deal with that level of delay on teleoperation. And so these are just different examples of where where I'm interested in, and this particular one was very compelling from that from that angle. The other thing I'll say is that, we've been biting off problems that were sort of spun off of sub-T, and that language one is definitely one of them. So how do we make robots actually be teammates? That's not something we're capable of right now. And so if we want to extend the capability of humans to cooperate with these robots, I think language is one of the big pillars for that problem. It's not the only one, but I think that it's a very interesting one, especially with recent advancements in generative AI.
Thank you. A question from Richard. What were the general reasons that objects were missed, i.e. the robot didn't recognize it or didn't get to the space?
Excellent question. So DARPA has some really crafty individuals at the organization, and they were trying to give us some softballs, all the teams some softballs, like a red backpack. It's kind of a softball. Like, a backpack can't really be ambiguous for something else. But what was pretty interesting was that they said, we also want to see if there are vents anywhere. And if you have like a vent, like from an HVAC system, like would be in an office, right? So usually these are like square like objects that have angles on them and everything. They're very hard to look at from LiDAR, so very hard to detect because they look planar. So LiDAR is not going to pick them up. And vision, actually, modern capabilities in computer vision don't really do well either because they're based on a technology called convolutional neural networks, and these convolutions are not good at determining sequences of quarters in centrality and location. And so, just one example of like pathological results that DARPA really juiced against us. So we had to like build out kind of innovative solutions in some of these cases. So yeah, sometimes our object detectors just didn't pick them up. That happened on more than one occasion. And that's where the human supervisor has to be sort of like always one eye everywhere. And we can't be sending this human supervisor thousands of potential, false reports. Look at this image, that'll take all day. And you can, that orange bar on the human supervisor capability would be like fully spent times a million, right? So we had to sort of kind of carefully tune for giving the human supervisor enough information, but sometimes we ended up doing a postmortem on the data. We did miss a couple of artifacts that we walked right past that our object detectors failed, and we did not flag it for the human supervisor to look at. But for the most part, the reason why we did not get all the objects was because we did not explore all the terrain. I think in the end, we got to like 65% coverage on the terrain, which is not great compared to the other teams. I mean, to the other two top teams, I think each one of them got in the 80s or so. And even there was a team below us that got to 90%, but that's where your capabilities for tuning around the human supervisor make a big difference. And that just goes to further develop the case that, these systems are not ready for autonomous operation purely. Like there needs to be humans involved all the time. And that's the case with every research project I've been with, every private outfit I've worked with, like there's always a human somewhere, right? And so I think that that's going to be the case for some time.
Great, thank you. Talking about the human interaction here, Gage asks, for the spot robot, did your team handle foot placement, planning / stability analysis? Uneven terrain and loose gravel seems very challenging. And if so, does this provide any information on the catastrophic fall that we saw?
Yeah, thanks, Gage. So no, the Boston Dynamics spot, like I mentioned, this was sort of a buy versus build decision. Many teams, and our original philosophy for robot building, if you will, was that we kind of had to control everything, right? We basically bought a platform that was just like a skateboard with motors on it. You can look at the Husky kind of like that. And we get to determine what the voltage across the motors is. So we really knew everything that was going on, right? Versus the spot where it's like we did no engineering beyond telling it kind of the direction where we wanted it to go, sitting at what are called command vels or velocities in a certain direction, and that was it. And for gate design, foot placement, all this other stuff, like I think that's a testament to Boston Dynamics' amazing engineering, like a really unbelievable product they've put out. And there were teams at the Subterranean Challenge that built their own quadrupeds, so they wanted that level of control over quadrupedal platforms. the first several competitions in which those platforms were fielded were abysmal. They saw a lot of failures: loose gravel, mud, water, anything. Like you name it, they fell on it. As the competition progressed, those teams did better with their quadrupedal platforms. But I think in the end, it's just really hard to have feedback loops that are fast enough for loose gravel. And in this case, when our robot fell, I think that was a case where there was a couple of things wrong. Loose ground was one of them, but also just like an aspect, and finally we put that huge backpack on the back of the spot, and that did change the center of gravity for the spot, for which there is actually a capability for us to change that in the control loops that Boston Dynamics puts on their spot. But we probably got the center of gravity wrong. I mean, that's how tight these tolerances were with quadrupedal operation in this environment.
Thank you. Question from Wilbur: how long do you anticipate it will take to actually deploy this technology in rescue operations?
Great question. Well, I think on the one hand, we have something today, right? And in cases where we literally can't send a human in, I think we could probably do it with the human supervision level and everything else, right? But in places where there's ever a replacement, like a human could do it, but the risk would be significant but not guaranteed, like terrible outcomes. I think there's a possibility that we would we'd be able to do this, I don't know, decade. I think that it depends more on it depends on more than just the science at some level. Like one issue with autonomous robotics has always been, like where is the break even point, if you will, to like develop this kind of technology to a commercializable aspect. And how frequently do we need to send in first responders, and how different are each one of those cases? As you can imagine, these are complicated questions that go beyond the science of what we're doing. And one can hope that maybe there's some multi-purpose type of capability that we can build into robots and then iterate on that. But that's not where autonomy is today. It's not even close. I think that we're much further away from that than 10 years. Like, hopefully by the end of my career, we'll be dreaming of something like that, is maybe one way to look at it. On the other hand, advancements happen in unexpected ways. I don't think anyone expected the capability of ChatGPT to be so close, right? And I think that, if you followed analyses on all this, then scientists have been surprised, about those outcomes. And I was surprised at the level of code gen capabilities that these things had. And so, I always am a little bit bearish on timelines, but also I'm an optimist. I think that some of these things can get solved more quickly than maybe we expect. Although some problems are pretty hard, but this one's a hard one.
Maybe a follow-up question that ties in nicely. Jay had asked if you have concerns that these robots may be used for war in the future or to overexploit resources.
Yeah, of course, absolutely. I mean, we all have that concern. I think that it's more than a legitimate concern, right? I've thought about this problem quite a bit. I've written some articles about it. My general sense of this problem is that it just always goes back to this, like scientists follow what are exciting, interesting problems. Where's the shiny nugget, right? I mean, and these are interesting problems. We can't change human nature when it comes to being interested in solving them. That's who we are. That's what science is, right? I think that while the concern is legitimate, we can't stop this stuff. It's actually impossible to stop it, I would argue. Stop the development of it, which means that we need to be safe about how we develop it. And I think that we're seeing that play out in real time right now, right? Like we're seeing what it means for generative AI capabilities to be potentially reined in, and companies that previously had that as part of their charter changing how they're thinking that might be possible. We're seeing, regulatory interest. I think that there's, a lot going on here. But the reality is, yeah, this is a threat. We can't ignore it. I think I'm not in the camp of this like ultimate pessimism, like evil AI is unavoidable. I think that's kind of a little bit strange. Like I don't know where that's coming from. I think that and people use tools, right? I mean, I think that's the other element to it. So and yet hopefully not with reckless abandon. I think there's many other frameworks we can look at international cooperation on things like that. So while I'm not an expert in the day-to-day of this, I can say I think about it a lot, and but I'm not pessimistic about it at this moment.
Thank you. A question from Groff, were all calculations performed on the robot, or were some performed on a server or cloud?
So for the Subterranean challenge, there were almost all of them were done on the robot. And the reason for that is that we sort of had as a default stance that we may not have comms capability for each robot. The robot will drop out of comms was the idea. And so that means that everything that is required for autonomous capabilities needs to be locally done. For that language problem, as I mentioned, we used ChatGPT, which means that we had an internet connection. I'm more and more believing that, the purely comms disabled case is fairly remote. Like internet connection is probably going to be available to us in 99.999% of applications. Even going so far as to like, I've heard of like internet on the moon and like GPS systems for the moon. Like, this is not science fiction. If we were thinking about like deploying, any kind of habitat somewhere or whatnot, there's going to probably be an internet connection, even on remote places. So yeah, I mean, maybe underwater would be one hard one. I mean, that would definitely be a hard one. But I'm not really too worried about most other cases right now. And the last thing I'll say is, I have been surprised by recent computing architectures to be able to run large language models locally. You can run it on your MacBook Pro these days, and even like a 70 billion parameter model. So I think that it's just a matter of time before we would move those capabilities that require an internet connection to something closer to the robot if needed. Oh, you're muted.
I just muted myself, I apologize. Question from Sam. When robots are exploring, I assume the maps they're developing are constantly updating. How do you deal with large discrepancies between objects in maps?
Yeah, that's a great one. So two answers to this. One is that we didn't have prior maps on those environments, and even if we did have them, we wouldn't know how to include them. Sort of an embarrassing reality. I mean, like humans, if you get a map, even if it's sketched out, you can do some pretty good work with it, right? You get a sort of idea in your mind about how this map might interact with your local surroundings. Current robotic technology, that is not possible. I can say that definitively. There's a lot of interest in solving that problem, but it doesn't exist yet. So changes in maps, not a big deal. If you were to give me maps in the robotics format, like the way the robots think about maps, not a drawing, but in those 3D reconstructions, scale correct and everything else, then there are a lot of ways that we deal with map discrepancies. And the biggest one being like your local result is useful, and then take pieces of those other metric results and stitch them onto the local result that you are getting right now. That's just one example. And there are many other ways to algorithmically to rectify prior stale maps against current understanding. But they are generally algorithm based. So something like figure out similarities between map 1 and map 2, and then try to stitch them together and ignore certain parts. There's not really a data-driven way to do that yet. And so that actually goes to a different question that I saw previously, which was that, what about how do we do like large foundation models for robotics, which is a really hard problem. And it's because our maps or our situated data on robots is so different than the sort of large corpora that are used to train large language models. By that, I mean, 3D maps are actually like a very different beast than words in a sentence. And so the architectures there might be different, but maybe not. Maybe we can use the same transformer-based architectures as an example. But the big difference is that, it's hard to collect enough data to scale on. And that's just one reason why we don't have sort of deep learning based techniques for that type of, discrepancy, working through discrepancies. Hopefully that answers your question.
Thank you. I'm going to close this out with the final question here. It seems like this may be from one of your former students. They write,
Okay.
A few years back, you said mobile robotics and autonomous driving was somewhere on the spectrum of rules-based and very predictable to something like a complex visual conversation between people and agents, and that if we wanted to make progress on the problem, we should hope that the problem is more on the side of rules-based. Do you feel this is still the case?
Oh man. Yeah, so thanks, Sam, for this question. Excellent. Yeah, I forget exactly when I said that and what context you had for that, or we had this conversation in, but just taking, my first stab at this today, I think that large language models is one example of, creating not reliable, but believable human input or output, human output, If you're given this circumstance at a three-way stop and, driver one approaches and then driver two approaches and, you sort of arrive between them, who goes first. Self-driving cars, that could be a pretty challenging problem. And I think for, anything that is relying on some kind of agent-based rule there, it gets to a little bit of like a, that self-driving car might be waiting there sometime. And, there is a way, I think, that we can still straddle the middle ground of rules-based while relying on some of these complex relationships between, agents on the road. In the end, I'm kind of moving away from the rule-based thing, primarily because, like we all have to cross double yellow lines to get around trash trucks now and again. And so clearly double yellow lines as a rule doesn't really scale well. And then, there exist many, many other cases in which we have to think on our feet a little bit. And so I think that, in these cases, we do have to rely on what is like appropriate behavior in that case. And I think that we have some new tools at our disposal since probably the last time you and I chatted to be able to handle that. And that's why I'm more interested in these foundation models. But thanks for the question. I'd love to chat more about it.
Wonderful. Well, Professor Heckman, thank you again so much for your time today and this amazing presentation.